Hi, everybody. Thank you so much for coming. So we're going to get started. We have some wonderful gentlemen from Facebook coming here, Lawrence and Daniil. And Daniil is going to start with a presentation on machine learning for satellite image analysis. Please give him a warm welcome.
Well, thank you everybody for being here. A couple of words about myself. I'm Daniil. I work in Facebook office in Boston, so if there's one thing that you remember about this presentation, please remember that Facebook office in Boston exists. That's very important for us. This is my team. Again, most of the team here in Boston, a couple of guys in California. Today we are going to talk about different aspects of machine learning and problems we see in mapping and satellite image processing. Why do we need to care about mapping at Facebook? Actually, if you're using Facebook applications, there are many places where you would see the background maps, like pages, events, check-ins, stories, some standalone applications where we show the maps. For different countries, and we have to cover the whole globe. So for different countries, we show mapping from different map providers. But quite recently, we started switching more and more to the map called OpenStreetMap. I'm not sure if you know much about it, but basically this is an open source map that everybody can contribute, everybody can use. It's supported by the community since about 2004. This is the way how OpenStreetMap grows. Unfortunately, I have a plot only till 2016, but right now it has about 12 billion on different nodes and objects into the map. So by the way, if you want to edit it yourself or contribute to it, it's very easy to do online. But the only problem, well, there are many problems, there's different kinds of solutions. There's several things that we do. First of all, we want to make sure, because it's easy to contribute, we want to make sure that it's not vandalized, right? There's no profanity. So we want to make sure that when we show you the map, they're like actual reasonable map. So basically, one part of the work that we do is just removing bad stuff from the map. That's how we call this whole stream of work. It's all cleaning. I'm going to talk about it a little bit later. But second part of work is that OpenStreetMap is still not complete. So we need to contribute to it. And the second part of the work that we do, the second pipeline, it basically adds the good stuff to the map. And this is what my team is mostly doing. So what about remove the bad stuff part? There's several ways how people can vandalize the map. The most obvious, you change the name of the street, there's something not pleasant. The less obvious, actually, you are playing Pokemon Go and just adding the lake next to your house just to make sure that your Pokemon will come to your house right there. For profanity checks, Facebook actually turns out to be very good with profanity checks. We have a long history of checking users' posts for that. So we have a very long list. You would never imagine that there are 39,000 words that could be offensive in the world in 43 languages. We validated basically all the names, the street names that come in OpenStreetMap. We validated, and initially we found about 84,000 of matches. Most of the matches are false. Most of the names are legit. And then we implement a bunch of rules on top of that. Who contributed to OpenStreetMap? There are like trusted users, trusted contributors. When was that contribution made, and so on and so forth. So in the end, we had about 2,000 suspicious names, 2,300 that we had to check by manually. And the result, we removed about 139 offending use cases. If you're interested about the distribution by languages and by locations, that's pretty much how they distribute throughout the world. Most of them were detected in English. I guess it's because most of the companies speak in English, but still we run through the checks in many languages. Actually, I speak Russian myself. I'm a little bit surprised that there are not a lot of Russians here. I should double check that later. Yeah. And then again, speaking of machine learning, if you go back to all those algorithms, you can basically imagine some of those things are simple searches. In some cases, we have to go through the pattern search because it's quite common for people to plug in, stars or spaces in the middle of the word to make sure they not pick up automatically. And we have a bunch of filters who resolve that. And it can go as far as to deep neural networks to try to detect those words reliably. This is a very interesting example of Manvoice, right? So before we were talking about detecting the words that people type in. Now somebody was really creative, right? So they took and they draw some words in kind of lakes, right? So any text recognition that we do would not be able to do it. So we have to do the optical. Basically, what we have to do, we render the map, and we have to do the optical character recognition in order to find those offending use cases. And just to give you the idea of the scale of this work, there are maps in general are served in tiles. Tiles are about 256 by 256 like pixel wide. And there are several billions of those tiles that cover the world. So basically we have to have a scalable system that would check several billions of tiles and run the optical recognition on top of that. For each tile we have a couple of probabilities. First is how confident we are that we detected the word here, how confident we are that we extracted correctly, and again, for many of those cases, there's a manual check to make sure that what we found is meaningful. There are a lot of very interesting software engineering problems behind that. Basically, so far I'm talking about the research part, how you can find it. But I'm the developer myself, so on our part is how you can scale it for how you can run all those algorithms in parallel, how to store the data. On our scale, this is like very, very challenging problems. So yeah, that's another interesting example where the optical character recognition picks up the word and tells us that the human should check it out. Now the part that I'm excited the most, okay, it's one thing to filter someone else's contribution, but it's much more exciting to be able to contribute ourselves. So when we are talking about OpenStreetMap, of course, we are serving it all over the globe. So let's talk a little bit about the coverage. And this is our sample assessment of the quality of the OpenStreetMap. How we did it, we just took a little sample throughout the world, compared it with different other mapping sources, and you can see that in most, in like United States or in Europe, the coverage of OpenStreetMap is really good. It goes up to like 80% or higher. But in Africa and some parts of Asia, it's the coverage is much lower. Sometimes it's less than 20%. And in Facebook, it's particularly important to have good coverage because a lot of our users live in these countries. So this is a general outline of our machine learning assisted pipeline to detect the roads. And there are several ways to approach road detection. The way how we do it, we first run the machine learning predictors that take the satellite imagery, I'll show you examples later on, analyze it, and try to locate the roads. Then we take those roads and process them into vectors, merge with existing OpenStreetMap data, and this is, as a developer, I'm always excited about like this part, like how to make this machinery, scalable machinery very exciting. But then probably the most important part happens here, because we have the team of human editors who would take a look at every change that we're introducing, triple check it, and contribute to the OpenStreetMap directly. This is a high-level idea of what we are doing there. So we start with the high-resolution satellite images. The resolution is about 59 centimeter per pixel, so you can resolve it very well. Then we run something that's called segmentation model. This is not the regular classification model. You know, in machine learning, there is a type of classification model that tells you what class of the problem you're looking at. This segmentation model actually gives you some answer per pixel. So for each pixel of the satellite image, we detected what is the probability that this pixel is a road, and what actually probability that this pixel is a house. I'll talk a bit about it later on. And this is deep neural network who's doing that. About 70 million parameters. We play with different models. Sometimes we work with ResNet, if you know what it is. Sometimes it's Deep Lab. But basically, very often we just take state-of-the-art the segmentation model is a black box. Plug it in and train a lot. There's a lot of training going into that. The complicated one of the complications of this whole process is that it's very hard, even for a human, to detect the road or the house on the map. So those are different areas have come from different parts of the world. And you can see that we can see all sort of problems here, from from the bad resolution to the cloud coverage to sometimes the roads are very hard to distinguish because of the shades and the overhanging trees. This is actually where the problem changed from the research to the production, and those are the problems that we'll see a lot in production. So the way how we handle it, technically, if you know machine learning, first thing that you do is you go generate training data. That's what we do. So what we do is sit, and like several people do, they basically ping the roads. And show us, so that shows very well to distinguish the pixel of the roads from the pixel of the backgrounds. And it turns out when we go to the new country, very often the roads really, the roads in the new country are different from the roads in the previous one. So we have to add more training data in order to make our models consistent. Right now we are working on one global model that would detect the roads in the whole world. But still, this is a work in process. Another interesting direction, because I was talking about OpenStreetMap, is can we use all those tags that people already generated for the OpenStreetMap as training data, right? Because somebody already said this is a road, so can you train on top of that? Again, this is a work in progress. Turns out you can do that, and it generates good results, except for sometimes they're misaligned with the satellite imagery. So in particular, for the road detection, as you can see here, you really need to align your labels really well. But this is a very exciting, like researchy kind of direction of our work. But going back to this particular thing, so somebody gave us the training data. Now you can go on and train the deep learning model. And this is a typical results, colors are switched here, but again, typical result per pixel probabilities that this particular pixel is a road. This is the raw starting point of our exploration. The next thing what we do, you would take those probabilities that go from 0 to 1, and you threshold them at some high threshold to make sure that you only detected the best rows in the set. Because you really don't want to introduce a lot of low data that you are not very confident about. But still you can see there are a lot of noise here, right? So now it's a binary data. It's like 0 for background, like 1 for the roads. But you can see a lot of disconnected pieces, a lot of noise. This is not something that we would like to give to our human editors. So the next stage is when we're trimming, connecting, merging. This is a whole bunch of heuristic and the regular kind of graph processing algorithms that would connect those, try to connect those things together through sometimes through the low confidence areas, and sometimes you just change corners a little bit, make the lines a little bit straight, and so on and so forth. And finally, you're dropping those little islands for look like noise here. Sometimes those islands of road, disconnected roads, still could be valid roads, but there's we usually hope that our human editors will add them back. Finally, we take this data and convert them to the vector OpenStreetMap compatible format. We also detect the kinds of the roads that we are contributing, because there are like 5 different kinds of the road, going from highway to the tracks. And the typical, if you compare before and after, so you can see on that side, you can see the OpenStreetMap roads before we contributed to that. And this is what we did after our automatic algorithm merged our contribution and the previous version of the OpenStreetMap together. And this is where the human work starts. So this is basically what our mappers see when they start working with the map. And now they have to manually check many of those new roads that we introduce and make sure that they're actually valid roads. We use this is our tool for the mappers. Actually, this is also the classic OpenStreetMap contribution tool. basically each human gets this little block of work, and they start like pull the machine learning roads that we generate, make sure that they're in place, and contribute to the OpenStreetMap. We have 3 roles in the mapping team. There are editors who do the editing, initial editing, validators who would validate the editor's work, and finally publishers who are responsible to contribute to OpenStreetMap. We also work with several teams across the globe, and it helps a lot when you like map in Thailand to have a team in Thailand who would do the work, because they understand the things on the ground much better. And in fact, so we get the feedback from those areas of the world. They could tell us, well, this is a strange object on the map that you're not sure about. This is actually the walking bridge. It's a very valid structure. Shifting gears a little bit. Okay, so let's say that we contributed the streets, the new roads to the world. But what about addresses, right? How can you generate those addresses? And this is a hard problem, basically. This is an open-ended problem. Nobody knows how to do it. You can think about trying to detect in the street names from the moving cars, right? To go the street views and trying to detect the name here. It's hard, and for many regions of the world, we do not have this data. So one of the things that we do, we're trying to crowdsource it, because there are about 2 billion of Facebook users. If a small fraction of them are willing to answer the questions about the map, it can contribute to the map a lot. So sometimes after people check into particular places, there's check-in mechanism in Facebook, we ask them the question, oh, by the way, which street are you on? Like, did we guess it correctly? And with this way, we crowdsource the street name contribution. Right now, there are about 176,000 of street names that we contributed this way. So going back to the question, how much mapping is left, how far it is, let me just bring you back to my original picture. Quite a lot, actually. Several companies contributing to the OpenStreetMap in parallel. Apple mostly working in the United States, Microsoft contributing a lot of houses in Australia. We just contributed Thailand, but we would imagine it will take several years before the whole world map is complete. In other projects, very related to the previous one, of course we can detect where the roads are, but we are also interested to see where people live in the world. So what we are doing in collaboration of the CSIN, which is the Center for International Earth Science Information Network, part of Columbia University, we are producing the high-resolution population density map. It works in a similar way how the road detection, but instead of roads, we detect the houses. And the CSIN can take our data that we generate and map it to the sensors that the government provide. And with this double-step process, we can actually have a very, very high resolution population density map for most of the world. Again, going back to my original neural network presentation, you can see there's yellow things here are the houses that we detected. And this is the initial step that would go into producing the high resolution population density map. Of course, it's hard for us to tell how many people live exactly in this house, right? That's why they're only the high-level aggregates. But compared to pretty much any other sources of the data, because other sources of the data would say there are 5 million people living in this province, as the province is 100,000 square kilometer bits. Compared to this source of data, our data are like way more precise. We can also use the population data to estimate the road coverage. So this is the result of our population density analysis for a particular area in Mexico. Covering about 23 square kilometers here. We can overlay it with a satellite image map and with OpenStreetMap to see, basically you would expect the more people live in the area, the more roads are there. So those two numbers are usually highly correlated. So if we see that there's an area with large population density, but with not a lot of roads, then we know that this area needs to be mapped urgently. So this is how we can prioritize our work to see which area of the world to map. Um, this is a normalized area. So after overlaying the population and the existing measure for the existing roads, we can see the areas that needs to be mapped. So the more intense the color is, the higher urgency it is to map this particular area. And the next very interesting metric is, so let's say we are not mapping uniformly, but only start mapping from the most important area with the most population. Turns out if you need to cover 80% of population of a particular area, this is how much you need to map. You just map this area, 80% of the population is happier. If you go to 90% of the population, this area needs to be increased. And then for 95 and 100% of the population to be covered, suddenly there's way more things that need to be mapped. So this whole process allows us to prioritize our efforts. But at the same time, you can see that to cover the whole world, there's a lot of efforts that need to be done. Couple of things that I'm not going to talk about today. Even though the contribution to OpenStreetMaps is online and pretty much you contribute to it, you see the result very soon after that. We are running a little bit behind the OpenStreetMap because we cannot afford any vandalization attempts there to propagate to our APIs, to our apps. So there's a whole project Manvoice that would allow to take, let's say we're running 2 months behind the OpenStreetMap, how to merge those massive changes that happens over the last couple of months. I'll probably leave this whole discussion to the next presentation, but the basic idea is that there's some kind of balance that we'd like to strike between the freshness of the map, we'd like to be as fresh as possible, and correctness to make sure that the map is not vandalized. Finally, to conclude my presentation, there's some, let me show the video that shows the efforts that we've done in Thailand. We've covered about 95 of the Thailand in the recent year. Well, just let me show how it happens. Well, so again, we are a Facebook team in Boston that contributing to maps a lot. He cares about mapping satellite images. Any questions for me? Please go ahead.
So I'd like to ask, so how much human validation effort is actually necessary in this, crucial in this process?
Quite a lot. I know there are companies who are contributing simply with human validation without any machine learning. Yeah. For us, we are speeding up the human contribution by about 60% by providing them with machine learning data. But again, everything needs to be like triple checked, because in the end, the cost of the mistake of contributing something that's not existing is very high. People are very sensitive in the OpenStreetMap community for us making mistakes. That's why literally there's like 3 levels of human checking before the contribution, and that's why our contribution actually very often are much higher quality than the rest of the community providing. Yeah, yeah. Well, there's one thing that I haven't talked about is like what kind of software do you need to in order to do those contributions, but that's separate talk. Yeah, go ahead.
When you're estimating population in urban areas where there's high rises and high-rise office buildings, how do you distinguish between an office building and an apartment building?
We don't. And this is actually much short answer for much longer discussion. This is exactly the question that we do. Like the same house in the rural areas, does it have the same number of people, high-rise, number of floors? We do have some estimates for the height of the building in the cities. So we have basically scale factor for different areas and we're trying to normalize our data according to those scale factors. But all our estimates are approximate. It's like we start with, I don't know, 10 million people live in Massachusetts and distribute them evenly across the state buildings. So, but if you want to contribute and talk about it more, I'll be happy to know your thoughts on the subject. Yeah, please go ahead.
What prompted Facebook to use like OpenStreetMap as their basis?
There are not that many map sources in the world. Google has really good maps, but guess what? It belongs to Google. Here is another provider of maps. There are a couple more like private providers, but OpenStreetMap seems to be the only open source and the most complete map in the world, in many areas of the world. So that was the main reason. Anyone else? Yeah, go ahead.
Yeah, let's say if we choose Thailand already, how can we decide which region you start first? Is it based on the image quality or is it based on...
Which region do we mapping first?
Yeah, like if we choose Thailand, the country already, and then like which section, like which city in the country you can start first? How would you decide?
There's several ways. I think we can like estimate where the greater need is, like looking at the population, looking at the Facebook user activity in those cities. But sometimes it's overlap with what our mapping team itself want to do when they think what regions are important. So basically several factors. Some that come from the signals from Facebook site. Some factors come from we honestly believe like you should start with Bangkok. So that's our first destination. Or quite the opposite, that first we would like to do the rural areas where there are less roads, so that our mappers get trained better, and then move to the cities. So there are several competing factors for that. Yeah, go ahead.
How often do you update the maps to account for changes in the roads?
This is so far we're doing the first pass over the map. So the update is a very important topic. But OpenStreetMap is community supported. So as you can see, even this video was comparison of how much we contribute to Thailand versus the community. So the idea is that once you bring the map coverage above a certain threshold, then the community actually is much better to contribute those small changes and do the real-time updates in the future. So our vision for the map, that in the end it's not going to be supported by us or Microsoft or Apple, that it will be supported by the community. That's the whole idea behind the project. Yeah, please go ahead.
How many users contribute with, like, for example, the street name contribution, and why do you think they contribute when they answer? When they ask, for example, is this the street you're in?
Mm-hmm.
How, like a percentage of people that reply to that or choose to skip it?
I do not have the numbers, but actually our first option is to skip it. Because we know that, first of all, if you do not give people this option, first of all, they will be unhappy with the experience. And second, they'll contribute the low quality data. So we basically the biggest button, just move on, I don't have to care. So I don't have the exact number, But usually there's a small number of like fraction of people that deeply care about maps and that they contribute. The good thing actually is that we have so many users, we don't need all of them. Even if the fraction of percent of the users contributing, that's way more than we need for what those particular map needs. Yeah.
So if I'm correct, you said you're training for road detection first, and if you want to do a new city, you need new training samples, right?
It depends. Usually if you're, all cities like in US, for example, are pretty much the same, right? You have asphalt on the road, you have, so yeah, you can take training data from one city, pretty much map another city. If you go to dramatically different country in Asia and Africa, then we need basically to get additional training data from the samples. And we show that it helps the training process a lot.
I just wonder, there is a software of computer vision which is called domain adaptation for using unlabeled information from a new domain.
Okay.
And using its unlabeled joking structure and stuff to utilize the existing model in a new domain or in a new country, in this example, for example.
Mhm.
I just wondered if there is this online research about it, because I
There you go.
think it was kind of applicable to
Mhm.
road detection that you mentioned. And I'm kind of interested in this domain adaptation service.
Wait, honestly, from the top of my head, like no idea, but we should talk more after the presentation. I'll be happy to share my like knowledge about which directions this whole like training research is going to. All right, thank you so much for your attention and for great questions. Okay.
Hi everyone, I'm Lawrence from Madson. I'm a researcher at Facebook AI Research. I'm based in New York, so Facebook Boston is awesome. If for some reason, like after you've studied here for a couple of years, you get bored with Boston and you want to move to a slightly bigger city but still enjoy the winter snow, then New York is the place for you. I'm going to be talking today a little bit about some of the work we've been doing, some of the research we've been doing in computer vision. By the way, if you have any questions, like it's a really small group, so like feel free to like interrupt me, just wave or whatever. Cool. So I'm in this group called Facebook AI Research. It's a group of about 200 researchers in Menlo Park, New York, Paris, and Montreal. And we're working on a wide range of problems around AI. I'm sure I don't have to explain you what AI is, right? I'm sure you've heard of some of the examples around maybe computer Go or digital assistants or self-driving cars, etc. And so one of the questions you may have is like, why does Facebook need AI, right? Well, I think Dan already did a great job in showing you sort of how AI is used in sort of a lot of processes, right? In the example he described, basically in constructing these maps, there's machine learning everywhere, right? In every stage of the process. But there are also more visible examples in Facebook products that you can see today if you use the Facebook app or any of our other apps. So an example of that would be something like translation. So about 50% of all Facebook users have at least one friend who uses a different native language. Likely this includes many of you. And as you've probably noticed, we automatically translate posts to sort of the setting that you use on Facebook. So just to give you an idea of sort of the scale of this kind of system, we translate almost 6 billion posts a day between about 2,000 different language pairs. So this is a nice sort of very visible example of like where AI is used today. A second example that you may not be familiar with is this. This is the Facebook Surround 360. It's an open source 360 camera. So what I mean by open source is you can go online and you can basically download like the entire tech specs, right? And so you order the components, and you can put this thing together at a really low cost compared to what it would cost if you would buy one in the store. And what it creates is something like this. So this is an example of a 360 video made in Grand Central Station in New York City. And so this 360 video was created using software that we open source, right? So we basically give you everything in order to be able to do this. A lot of people are very excited, I think, about, I don't know, this somebody with this camera standing in the middle of the station. And why do we give all of this away? Well, because we wanted to make it easy for people and content producers to make these kinds of 360 videos and sort of share them with the world. A third example I want to show you, and now I'm going to keep my fingers crossed that the sound works, is an example of a product that is aimed at visually impaired users of Facebook.
Every day, billions of photos are uploaded to our family of apps. To help open our platform to everyone, we use AI to help describe photos that visually impaired members of our community can't see.
Getting ready for tonight's game. Image may contain one hour people playing sports, choosing outdoor.
Now, these captions paint a more vivid picture than ever before by using active language.
Mickey's starting to get the hang of his smiley. Image may contain one hour people riding bicycles, bicycle and outdoor.
Our AI can describe someone playing an instrument, eating with their friends, or standing on stage.
When a rain show last night, image may contain one person on stage and playing a musical instrument.
The future is happening now, and we're just getting started.
So this is an example where we use computer vision to basically make newsfeed more engaging for visually impaired users. Just to give you a sense of the scale of that, there are about 35 million visually impaired users who would be potential customers for a tool like this. And so it's basically combining vision with text-to-speech on the phone. So what is underlying this? I want to talk a little bit more about some of the underlying models here. So essentially what is happening in this last example is a kind of image classification. So in image classification, the task you're trying to solve is you're given an image, a photo, and you're trying to recognize what is present on the photo, right? And typically this is framed as a classification problem where you have a large range of visual classes that you want to recognize. And sort of the workhorse of modern computer vision, so sort of the core model that people use to solve these kinds of problems are these things called convolutional neural networks. So there are a lot of different ones. You may have seen or heard some of these names. But basically what it is it's something that, it's a model that repeatedly filters the image in order to progressively sort of create a representation of the image that contains semantic information, right? So that contains information about the content, but nothing else. And these filters, they're learned on labeled training images, right? So Daniel just showed you a nice example of, sort of labeled training images for satellite images. In the case of this product for visually impaired users, it would be images that are labeled for the content that is present in the image. So just to dive in a little bit more, this is my one slide introduction to convolutional networks. So this is basically what a convolutional network does. It starts from an image. An image is really a thing that has three channels, a red, green, and blue channel, and you have intensity values in each of these channels, right? And so now what we're going to do is we're going to filter this image, and we're going to filter it with a set of convolutional filters, and by doing that, we create basically a new image. And this image will typically have more channels. It won't have 3 channels anymore, but maybe, in this example, it has 4. In practice, it would maybe be 128 or 256 channels, so many, many more. But each of these channels contains a filtered version of the image representation in the layer before, right? In this case, of the input image. And so you can sort of, if you look at it, you can still sort of see the cat in this filter representation, right? Now, after we have applied this filter, we're going to apply a nonlinearity, and now we're going to filter sort of the new image again, right? Like this representation in the middle, it's essentially another image, and so we can filter it again. The reason, does anyone know why do we put the nonlinearity in the middle? Any ideas? Yeah? Oh.
No one answers. Basically decompose it to one page multiply.
Exactly. So filtering is a linear thing, and if you do a linear thing and then you do another linear thing, you just did one linear thing, right? And so you need to somehow make it nonlinear in order to be able to get sort of the, the expressive models that you need in order to make prediction. And so that's why there's always like this nonlinear operation in these deep networks. So in a convolutional networks, we're repeating this over and over again, right? So there are like 50 or 60 layers of these like, filters with nonlinearities, right? But that's really all that's happening. There's one other key component in these models, and that's a component that's known as pooling. So what you see in sort of this example is that when I filter, I maintain the sort of spatial structure of the image, right? There's still sort of location information. And at the end of the day, I'm not really interested in where something is located in the image. I'm just interested in what is in the image, right? And so progressively over time, I want to remove spatial information from the image representation. And that is what pooling is doing. So what pooling is really saying is, I'm going to take a part of a channel, of a feature map, and I'm just going to take an average value over it, or a max value over it. And so what that's doing is it's basically aggregating information into like a single value, right? It's removing some of the spatial information. And so if you do this a couple of times, what you end up with is essentially with a feature vector, right? Just a set of numbers that somehow contain some information on what was present in the image, right? And once you have this feature vector, you can essentially apply a standard linear classifier, right? So something like a logistic regression classifier. And what that will give you is it'll give you a distribution over the classes, right? So in this case, for our current setting of the filters and the linear regressor, what this model has predicted is that there's a 20% probability that there is a dog in this image, a 70% probability that there's a cat, and a 10% probability that it's a tree, right? So this is a fairly good model, right? Like if you were to output the most likely prediction, it would correctly recognize this image. So this is how you run a convolutional network. Now, how do you train it? Well, if you're training a convolutional network, for this image, you would have annotated that there's a cat in it, right? And so you can compute some kind of error or a loss, right? You know that this model should really have predicted cat with probability 1 and all the other classes with probability 0, right? And so I can compute some kind of error saying, well, your score for cat was 0.3 too low and your score for dog was 0.2 too high, right? And so now what we can do is we can start asking the question, how should we change this linear regressor in such a way that if I were to run the same image through this network again, I would get a slightly better prediction. I would get a slightly lower error. And the way you do this is by computing the gradient of this error, right? So it's really sort of, in a sense, it's really high school mathematics almost, right? You have a function, this error that you want to minimize, and the way you do it is by computing a gradient, computing a derivative, and trying to go down, right? In neural networks, this process is known as backprop, right? So what backprop is doing is it's basically for the regressor and for each of the filters, it's trying to compute how to change the filters in such a way that if I were to run this particular image through again, I would have a slightly lower error, right? So once I've run this backprop thing, I now have a model that's slightly better for this particular image, right? That's the only thing I have. So now what training is, it's really quite simple. You repeat this a gazillion times, right? for many, many different images, right? Because, you know, we don't care about being correct on this image. We want to be correct basically on all the images, right? And sort of the technical term for this is stochastic gradient descent, but it's really, you know, keep on trying until you get somewhere that works. Does this make sense? Cool. So one of the things that we sort of work on a lot inside Facebook AI research is on what should the architecture of these convolutional networks be, right? Like how do you connect up these things? And on a very high level, you can think of convolution, sort of most of the early convolutional networks, so things like LaNet, which was sort of the first, you know, real convolutional network in the early 90s. That looked something like this. So this is exactly what I just explained to you, right? You have a set of channels, you do some filtering, now you get new channels, you filter again, you get new channels, etc. Now, a couple of years ago, there was a very influential paper on something called residual connectivity. So the idea was to basically add what are called shortcut connections. So the idea was to not only like basically the output of each block, of each layer in the convolutional network was not just going to be the output of the convolutional filter, but it was going to be the output of the convolutional filter plus the input, which is kind of funny, right? Kind of weird. So the reason, but what turns out is that this works much better. And the reason that this works better, it's a little bit technical, but it has to do with the way that backprop works. It has to do with the sort of the amount of information that you get from sort of the error into early layers. So what's happening is that the sort of the gradient of the error through these shortcut connections, it gets copied. And so each layer in this network gets sort of direct information on like, okay, this filter contributed this much to the error. And it turns out that that makes learning these models much, much easier, in particular if the models are very deep. And in practice, these models are very deep, right? So, a practical model would maybe have like 50 of these convolutional layers. Now, we were playing around with these things because this is sort of the state of the art, right? And so what we noticed at some point was something really weird. So we would train up one of these residual models, and now at test time, like when we're running it, we would just sort of remove this entire layer. And so we would just connect like the red guys over here to the dark blue guys over here, which was kind of a crazy experiment, right? Like why would that work? And much to our surprise, it just worked. So you can take a ResNet, you can remove an entire block after you train the thing, and nothing breaks, which is kind of bizarre to us, right? Like, you know, if I do that with anything else, right? If I remove a part, it's gonna break. And so we were thinking about like what is happening here, right? And so what turns out is that the sort of the norm of the output here is very small compared to the norm of the information that flows through here. And so we do a lot of work computing a convolution, and then we basically sort of add it to values that are much, much, much larger, right? And so we're almost throwing away the results, which is very bizarre, and it suggests that these kinds of models are actually not very computationally efficient. Or, you know, it sort of gives you hope that there are much more efficient models out there. So our hypothesis was, well, you know, maybe what these models want to do is they want two things. On the one hand, they want to, like in each layer, construct new features that contain more information on sort of the semantic content of the image. But maybe they also want to sort of keep the old features, right? And that's why they like copy them with like a very high norm through these shortcut connections. So then we were thinking, well, you know, if we want a model to keep access to the old features, to features in earlier layers in the model, we can do that directly. And so we came up with this model called DenseNet, where, you know, basically everything connects to everything. And so what this looks really weird at first, right? Because what this means is basically you get sort of a network where you get more and more features over time. But what we found is that you can actually make these networks really, really slim. So you can only you can sort of make them in such a way that there are only very few channels in each layer. So I will switch to a different representation just to give you a better idea of what these dense nets are computing. So the idea is the following. You start from your input channels and you apply sort of your convolutional block, and this gives you some output channels. But compared to something like a ResNet, the number of output channels is very, very small. And now we concatenate. So we concatenate the output channels with the input channels. And now we do it again. We apply a convolution on sort of this new representation. This gives us the red channels, and we concatenate, right? And we just repeat this process. And so we have a network that sort of grows like this, which is a little bizarre. But what it is doing is basically at every layer in the network, you have access to all the information from all the previous layers, right? So that's sort of the core idea behind these models. And this just keeps going. And so, you know, maybe at first it seems really weird, right? Because now my network is growing sort of as I make it deeper. But what we found in practice is that it's actually more efficient than these residual networks. So these are results on the ImageNet dataset, which is sort of a standard benchmark in academia and in industry for testing out these image classification systems. So what I'm showing you on the y-axis is the classification error, so lower is better. And what I show you on the x-axis is on the left side the number of parameters in the model, and on the y-axis the number of flops that you need in order to sort of run an example image through the model, right? And so what you see here is that, you know, these dense nets are actually more efficient, right? Like they get you to the same accuracy with fewer parameters and with fewer flops. What you also see is that if you make these models bigger, right, they get better. This is true for both residual and dense networks, which is interesting. Now, in order to be able to do these kinds of experiments, there's a lot of infrastructure work that goes into that. And I want to say a little bit about what we sort of do in this space. So we build our own GPU servers. This server is called Big Basin. It's a server with 8 GPUs. And it's actually open sourced. So what that means is you can go online, you can download the technical specifications, you can order the parts, and it'll be a lot cheaper than what you buy from NVIDIA. On the software side, we built PyTorch, which is a deep learning framework that maybe some of you have used. And so, you know, you can, if you want to spend some, if you can get your supervisor to spend some money, you can work on exactly the same infra as us. It's still not cheap, but you know, it's cheaper than NVIDIA. And sort of doing this kind of work in-house really allowed us to scale up. So recently we published a study where we trained these convolutional networks on 3.5 billion images, which is sort of orders of magnitude bigger than what people have done before. And what we sort of see, what we saw in those experiments is that the accuracy on target tasks, on the classification tasks, basically increases sort of log linearly with the data set size. So here again, on the y-axis, I'm now showing accuracy, so higher is better. I'm sorry for switching that around. And on the x-axis, I'm showing the number of training images that we use for training. And note that that is on a logarithmic scale. So this is like 1 billion, and this is 3.5 billion images. And so what you see is that, you know, as you add more data in this training process, your models get better and better. And this is actually currently the state of the art on the ImageNet dataset. It's more than 2% better than Google, which we're very happy about. So, you know, this just gives you a gist of some of the work that we do in image classification. Of course, there are many other problems in computer vision. So this is work by colleagues of mine who worked on detection and segmentation. This is a model called MOSCAR-CNN. The core sort of underlying ConvNet is the same, but there are different sort of prediction models on top in order to be able to produce sort of, you know, pixel exact segmentations of objects as well as bounding boxes, and you cannot really read them, but there are labels there as well, right? And so this allows us to get, sort of a deeper understanding of what is depicted in an image. Another project by colleagues of mine is called Denspose, and I'll just show you a little video of what that does. So basically what this is a model that tracks a couple of 100 points on the human body as accurately as possible. This is a fun video, right, to try it out on. So as you see, I mean, it works pretty well. So what could you do with this? Well, you could imagine what Boston would look like if everybody wore exactly the same shirts or was walking around in their underwear. Now, it's not perfect yet, right? But you can imagine as this kind of stuff improves that there are a lot of actually nice and serious applications to this, right? In particular, think about buying clothes online and having to send them back every time because they don't look nice on you. This would allow you to to try it out virtually, right? So there are sort of real applications lying behind this. Are there any questions about this part before I continue? Sure, yeah.
Yeah, I was wondering what's the next step to improve the accuracy, because right now it's like 80 something, right? So how would you like tweak the hyperparameter, or would you like change the architecture?
If I knew, I'd be working on it right now. It's a great question. I mean, on a data set like ImageNet, I think the accuracy is pretty much saturated. In the sense that if you look at so the error rate is 14% right now of our best model. But if you look at the errors, they're not really errors in this order. I mean, they're errors, but they're of the type, you have two dog breeds that I cannot even tell apart as a human, and it confuses them, right? And maybe there's like 3 dog experts in the United States who can tell you why this is a different dog than the other one. But I guess my point is that 14% error is actually much smaller than it seems. So I think in terms of what we need to do next is 2 things. One, we want to recognize many more things, right? So in a data set like ImageNet, you have 1,000 classes, but in the world there are around 1 million different man-made objects. And there are about 200,000, different plants and animals. And so, you really need to go and recognize 1.2 million things rather than 1,000 things, right? And so there's still a lot of work that needs to be done. The other part is, the other open question I think is, and I'll get to that in a minute, is around what do we do next? Right? So like if we recognize all the objects in an image, does that mean we understand the image? And I would argue that you can recognize all the objects, but really not understand what's going on in the image. And so they're like going to sort of a higher level understanding of images. That's still very much an open problem. Yes.
Hi. What you mentioned about ResNet and also DensNet, and when it comes to, and question about the benchmarking. How do they perform when you do side by side benchmarking? That's what was a lot faster?
You mean in a practical implementation?
Yes.
Oh, that's a good question. I mean, practical implementations are really benchmarking practical implications is really complicated because there's a whole stack of developers who are optimizing a particular model. So to give you a concrete example of this, after the DenseNet work was published, we got a lot of feedback that the DenseNet models are very memory inefficient. And this is actually completely untrue. If you implement them well with sort of strided tensors and so on, you can implement them in ways that are much more memory efficient than any other model out there. However, you need to do convolutions on strided tensors. And that is possible, like NVIDIA has implemented this, but they've never optimized it, right? And so if on a GPU you would try it out, then you would conclude, oh, it's very slow. But it's very slow because, you know, there were probably 100 NVIDIA engineers who worked for a year to optimize ResNets, and they worked for 0 minutes to optimize dense nets, right? And so that makes these kinds of comparisons really, really hard. Also, it depends a lot on where, you know, on what platform you're going to run these models, right? We do training on GPUs, but actually models when we do inference, so when we do prediction, these models will either run on a phone or they will run on a CPU. And so they will run on a completely different computational platform, right? So it's a very complicated question to answer, I'd say. Thanks. Yes?
How much are you moving towards natural language generation, and have you considered reverse engineering the process to use like image captions to then predict possible objects in language?
Yeah, so we have actually tried some of that. In particular, so in sort of the scaling, in the study where we scale up, we use our hashtags because they're a little bit more structured. And so we use those as targets for the images. We've also played around with trying to use sort of words or n-grams in captions. It's a little bit harder because there's so much noise in those things, right? But it's certainly an interesting avenue to try out. Yeah. Yes.
I'm curious about like what ways you guys are like using to kind of like better your descriptions of the images for the visually impaired, and like what.
So in the product right now, in the sort of the version I showed, it's a very simple thing, right? It'll try and recognize classes and then read out the classes. And it actually, you maybe notice it sounds a little funny, right? It says image may contain X or Y. Which is basically what happens as soon as you get lawyers involved in a project. Because they're very concerned about, about messing up, right? You know, even if your models have, 0.1% error rates, because we have so many users, there are going to be errors out there in the real world, and the errors can be very unfortunate. And so you want to be very, very careful about basically which classes you recognize in such a product, and also sort of how high you put the bar for outputting a prediction. Right? And if you go to captioning, this gets way harder, right? Because now you have very little control over what this model is going to generate. And I guess Microsoft had a nice example of this with their Thai chatbot last year. I mean, this can go bad very, very quickly. Yeah, great question. Cool. Okay, so in sort of the last 5 minutes or 10 minutes or so, I'm going to get back a little bit more on your question, which is basically what's next, right? If we recognize all the objects, do we actually understand the image? And I would argue that the answer to this question is probably no, right? So here are some images. Our models for the top image would probably recognize, that this is a shadow. But we as humans would infer much more from this image, right? We would infer that this is probably a couple that are in love, right? Like they're probably not, business partners or something like that. And if we would give these bottom two images to our system, they would say, oh, this is a lion in the grass. Right? But what they wouldn't recognize is that, in this scenario, I should be much more worried than in this scenario, right? And so there's a lot of sort of subtlety and sort of higher level information in images that these systems right now are not getting out of there. So one of the questions as you start thinking about this is, how would you, as you start thinking about visual understanding, is basically the question, how do you measure this? How do you measure whether you understand an image? The nice thing about image classification is, we can measure some classification error, and that's a reasonable, reliable measure for the thing we're interested in. But how do you measure understanding, right? That's actually a really hard problem. So one of the proposals that's gotten some traction in the past couple of years is this proposal of visual question answering. So the task is like this. You get an image, and you get a question about that image in natural language, and you're supposed to answer that question. Right, so in the top left case, the question is what is the color of the jacket, and the answer is red and blue, right? And so this seems like a reasonable proposal, right? If you really understand the content of an image, you should be able to answer any question about that image that I ask you, right? It's kind of like a Turing test for visual questions. And so people got really excited about this, and they started to build models, right? Because that's what machine learners and computer vision people do. So they would take the image, they would feed it through a convnet, produce some image features. They would take the question, they would feed it through some recurrent neural network, like an LSTM, and that would produce a question feature representation. And then they would combine these and feed them to some classification model to try and predict the answer, right? And this actually seemed to work somewhat nicely, right? So these were numbers that people got on a task where you have a multiple choice questions with 4 possible answers, right? So randomly guessing would give you 25% accuracy. But if you use a system like this, you can answer 52% of the questions correctly, right? So you seem to have been making some progress. Now, we were looking at this and we got really concerned. And the reason we got concerned is because of this horse. Has any one of you heard the story of Clever Hans? So this is Clever Hans. He was a horse that lived in the early 1900s in Germany. And it was a quite amazing horse because you could give him an arithmetic assignment and he could answer it. So you could ask him, Hans, tell me what 2 plus 4 is. And Hans would tap his leg 6 times. And whatever you asked him, he would get it right. It was really amazing. And so his owner, he of course saw a business opportunity. And so he took Hans to, markets all across Europe where people would pay to see this amazing clever horse. Now, of course, at some point, some people got suspicious, right? They got wondering, what's going on here? Is this actually a smart horse? And so there was an investigator called Oscar Pfingst, and he, after like a year and a half of research, he unraveled the mystery. So here's the strategy that the horse had learned. The horse would wait until the question was asked, and then he would start tapping his leg until the audience sort of started cheering, and then he would stop. And he would get every question correct, right? So why am I telling this story? The reason I'm telling this story is because it shows that it may be able to, solve questions, right, or answer questions that seemingly, seem to require intelligence without being intelligent at all, right? And so we were wondering, these visual question answering systems, are they also horses, right? Are they like Clever Hans? So we did the following experiment. We took one of these multiple choice visual questions and we threw away the image and we threw away the question. So we would only keep the answers. And now we would encode the answers with word-to-vec features, so some very basic semantic feature. And we would train a binary classifier to say, is this the answer or not? Right? Without looking at the question, without looking at the image, and without knowing what the question is. Right? And at test time, we would just sort of give it the 4 answers. We would score them with our binary classifier, yay or nay, and we would predict the highest scoring answer. Right? Very simple. Here's how it does. That's pretty amazing, right? So what has happened here? Well, what happened here is that it turns out that gathering a data set like this is actually really hard. So it turns out there are all sorts of natural statistical biases in the world that are reflected in these data sets. For instance, if I ask you, when was this picture taken, without showing you the picture, you should always say during the day, because there are more pictures that are taken during the day than at night. Or another example would be, and this has to do with the way these data sets are collected. So the way they collected the data sets was they would give an image to a human annotator, and they would ask the annotator ask a question about the image. And so that's how the questions were generated. Now, for instance, the question, what is covering the ground? It turns out that question only gets asked when there are leaves on the ground, right? And so if you see that question and then you have 4 possible answers, you know the answer is always going to be leaves, right? And so what we did was basically in our simple model, we were smarter about exploiting those statistical biases, right? And so that way we could create this clever Hans model that, you know, that sort of beat the sort of an actual deep learning model at the time. Now, of course, you know, if you add the image and the question, you know, into sort of this model, of course that helps, right? And so, you know, you get a better model this way, but that was not really the point of this study. Since then, like one of the things we've been working on is this data set, which is a purely synthetic data set called Clever. This is sort of in homage to Clever Hans. We really had to work very hard to make it an abbreviation of something meaningful. And so what it is basically these images of like, you know, different objects with questions about them. But because everything here is synthetic, and we can sort of, what we can do is we can, you know, sample images and sample questions, and then do rejection sampling to make sure that there are no biases in these in this data set, right? So what we have here is a data set where the only way in which you can answer the question is by looking at the image content. There's just no other way. There's no other information that you can explore. And so we've been doing analysis on data sets like this, and so that taught us a lot about sort of the existing visual question answering models. For instance, that they can recognize attributes, so they can recognize that something is blue or round or small or big, but they cannot compare them. So if you ask them, you know, is this the same color as this? They don't really know what's going on, right? And so this is suggesting that maybe these models need some kind of memory, right? They need to remember the color of one thing to be able to compare it with the other thing. Systems cannot count very well, but what they can do is comparing sets of integers, and the way they do it is by, you know, by basically always picking the smaller integer. Right? Because there are, you know, there's always still a sort of Zipfian distribution in terms of the number of things that are somewhere, right? Now, what we've been using this data set for is also to study sort of new families of neural networks. So the idea behind those neural networks is the following. We take the question and we parse it through one of these LSTM models. And what we produce from that question is we produce a very simple program. So we're basically trying to predict what is the program, what are sort of the reasoning steps that you'd have to perform in order to answer the question. Right? So the question in this case is, are there more cubes than yellow things? And so the reasoning steps that you'd have to perform in order to answer this question is, so this is a program in prefix notation, you'd have to take a scene, you'd have to filter out cubes, and you'd have to count the number of cubes. Now you'd have to take the scene again. You'd have to filter by yellow color, and you'd have to count the number of yellow things. And now you have to compare the two, right? So you have to do a greater than. So what we predict is we predict this program from the question, and now we do the following. Each of these functions here, each of these sort of, you know, program elements, we're going to encode with a small neural network. And so we're basically going to we're going to implement them with a small neural network. And so for a given question, we're going to compose these things, right? So now the neural network structure is a function of what the question is. Every time you ask a different question, you get sort of a different composition of these neural modules. And so you're running a different network, right? And so this is an attempt at, you know, trying to more explicitly put reasoning into these neural network models. So in this case, you know, it gets it correct. Beautiful, great. And on a data set like Clever, this actually works quite nicely. In practice, it's so much harder to make these work because we still haven't solved the problem of visual question answering data sets sort of in the real world. But at least in the Clever case, this seems very promising. So just to conclude, I hope sort of what Daniel and I have showed you in these talks is that at Facebook, we really sort of work on all aspects of AI, from research to infrastructure to applications in the real world to all sorts of products. And with that, I'm happy to take any questions that you still might have. Thanks. Yes.
Did you test whether the synthetic data set is susceptible to the same kind of predictor as the original DQA?
Yeah, so sort of the test that we did was basically, we would generate a version of the data set, and then we would run our cheating models, our clever Hans models, and the first couple of times they would still sort of do better than random. And we would have to think really hard about like what bias could it be exploiting. It turns out to be really hard to make a truly unbiased data set. And so we iterated a couple of times, and so now sort of our stupid cheating model doesn't work on clever, right? It produces sort of random records.
Okay. Interesting. What kind of biases maybe could you say?
So there are more subtle things. Like if I ask you, what is the color of the thing to the left of some other thing? Now, the official reasoning steps would be you find the other thing, you look left of it, and you find the thing there. Right? But if you're somehow incapable of performing those reasoning steps, your best bet would be to just look in the left of the image and find a thing. Right? And so those kinds of biases are really hard to weed out. Yes.
When you made incorrect predictions, like for the DQA situation, were you generating like saliency maps to look at why things were happening the way they were, or not really?
Not really. I mean, yeah, no, we haven't really done that. I don't have a very strong opinion on the saliency maps. Cool. Well, thanks very much.